did you attempt to do anything else? Like just play around on the app? Okay, never mind.
No,
Okay, so first, yeah, sorry, you were saying.
nothing. Let's continue.
Okay, so I guess the rest of the people are depending on the recording. So we'll start for now. So this is the second class of your PLC lab, and in this we're going to go over, like I'm just going to show, since no one has done the full adder subtractor, so I'm just going to show you the implementation, and like I can't make it right now because it's going to take a lot of time to explain the logic, but so I'm just going to present it, and then we're going to explain a few certain concepts that are very important, and then we're going to just do practice sums on all of the topics for once, so you get a clear idea of everything. So, can you see my screen?
Yeah.
Okay, so we're going to start with the first. Okay, so um, uh, this is the circuit diagram using gates, our basic logic gates of the full adder, and this is the truth table. So now I'm just going to show you the basic implementation on trilogy. Okay, so see here, you know that there are going to be three inputs and two outputs. Your A and B are the units that you're going to add. Your C in is the carry forward from your previous addition. Your S is the sum, and your C out is the remainder. So now, like obviously you know all this. This has been taught in DST, so I'm just going to go over it quickly. So now, basically, you'll have to make two, like as we explained in the last class, for one rung for one rung of your ladder logic, you can only use one output. Otherwise, the program just gets messed up and it'll just randomly choose between either of the two. So you have to make each separate rung for the two outputs. So since here we have two outputs, we're going to make one for sum and one for C out. And obviously, our three inputs are going to be A, B, and Cn. So usually how you go about these kinds of programming is when you have the truth table, you're going to, suppose you're making it for S, you're going to see where S is 1 and where you need the output to be 1, and those cases you're going to catch on to. Like suppose the first case over here, S is 1 when my A and B are 0 and Cn is 1. So the first case of that, when A and B are 0, like you can see it over here. So if I give A and B 0, these two are still going to be normally closed. And if I give C in as 1, this normally open is going to turn into a normally closed, which will give me the one I need over here, which satisfies this first condition where my S is 1. The same way, when it's 0, 1, and 0. So I need to be giving 0, 1, and 0. You can recognize by whichever inverted gates are there. Like suppose if I'm giving 0, it means that it needs to be a normally closed switch already. So this is 0, this is 1, and this is 0. When I give this certain input to this rung, I'm going to get my output as 1. And so here you can see there are four cases, 1, 2, 3, and 4 for S to be 1. So that's why we have it just exactly implemented those three cases. Because in all of the other cases, like suppose if you were to say 0, 1, and 1, so that would mean that A is inverted and 0, 0. That case doesn't exist here, so my sum is never going to be 1 in that situation. The same thing for C out. Suppose if you catch this. So the logic you should know of this, what it should be. It should be 1, 1, and 0. So at 1, 1, and 0, my C out should be 1. So as you can see at 1, 1, and 0, my C out is 1. So you just, whenever you have the truth table, the most straightforward approach is like where you don't have to implement that much of logic. Just catch on to the cases wherever your output is 1 and implement only those in your rung, and you'll easily get the answer. So like if you want, I'll simulate and show this to you. Okay. So we're going to try a case in which both are 1 first. So, okay. So we'll try all three as 1. I'm going to make this one, and this one. So as you can see, my sum and my C out both are 1. Now next we're gonna try this case. Oh, sorry. We're gonna try this case when it's 1, 0, 0, and my S is 1 and C is 0. So we'll try 1, 0, and 0. So my S should be 1 and my C out is 0. Because, and like it's happening so easily because I have just selected those cases where my output is going to be 1 and implemented those. Like, of course, there are many ways to go about this kind of programming, but this is the most straightforward approach. Now, the same thing for full subtractor. I'll just show you the circuit quickly. Okay. So here also, this is the difference and this B out. So BN is your carry forward of the previous one. The difference is your answer, and B out is the extra that you need to consider. So yeah, so this is the XY, which are the numbers that are going to be subtracted. And as I said that you need to make two different rungs for both of them. So that's why we have made a separate one for D and a separate one for B out. And also here also in the truth table wherever my difference is 1. So like in these 4 cases, I have implemented only those 4 cases, and the same logic as the full adder is going to give me the output that I need. Okay, so let's try 0 1 0, in which both should be 1. Okay, so 0 1 0, yeah, so my D and B out both are going to be 1, because I think in this one and this one is giving me a complete circuit. No, and this one's giving me a complete circuit, and I think the third one over here. And the same way, if we were to take another case, let's take 0 0 1. So 0 0 and 1, yeah. So wait, 0 0 1, I should get. Oh, there's some issue over here. Okay, never mind. At least you all got the gist of it. I think it's
You are
some.
checking it wrong way. See the B in value and A B value because here A and B
Ha,
is
yeah.
the X
Oh,
and Y.
yeah, yeah, yeah. Okay, so never mind. I've just labeled it wrong. But you get the gist of it. It's the same thing as the full adder. Just catch the basic principle, like I said, just catch on wherever your output is 1, and just simulate it, just make the rungs according to that. Does anyone have any doubts in these two?
No.
Okay. So now we're going to talk about another very important concept, which is called latching. So there are, okay, so imagine a situation where you only have a push button, but you need a continuous flow of your output. Now, the only way, like there are two ways. The only way, the one very rough way is that you continuously keep on pressing the push button, which is, of course, no one's going to have time for that. Suppose you need it long for like 2 hours, you need it on for that much time, you're not going to have someone holding the button. So, the another way in programming where you can do is, so this is basically like a recursive function, okay, to make it easier for you to understand. This is my input. Let's consider this is a push button. Okay. So as soon as I press my A, this normally open switch is going to become a normally closed switch. This ladder is going to, I mean, this rung is going to become a closed circuit, and my output is going to become high. Now, as soon as my output becomes high, as you can see over here, the same function I have added as input. Like it's the same name. So as long as when this gets high, even this is going to get high, and when it does, this normally open is going to become a normally closed. Now even if I leave this
1 minute.
button, yeah,
What gets high? Uh,
um
which
okay,
one? The
so
circular one or the
my output
rectangular
my output
output?
the coil. So when I trigger this button, which is my push button of input A, this normally open becomes a normally closed switch. This is going to become a closed circuit. That's why my output here, the circular coil, is going to get high. And as soon as my output gets high, I'm also giving the same value as input. So if this is high, of course, even this is going to be high. And when this gets high, it's going to become a normally closed switch. So even if I were to release my input A, like if I were to make this 0 again, then my current still has an alternative path, and it just becomes a recursive function on its own, because it's supplying input to itself. It just needed a trigger before, and then it just keeps on applying it to itself. So I'm just going to show you the implementation of this. Okay, so we're gonna add our input A and another stop switch, because we always need to implement this in our circuit, and a coil, which we're going to name O. Now to this A, I'm going to add a parallel, and I'm going to um, put the same thing, but it's going, see, if I add it parallel to one of my inputs, of course it's going to act as an input function. I didn't like, wait, I'll show you again. See, here it didn't, even though I'm not changing it to input, I'm still keeping it as output only, and I just press enter over here. Yeah, and it gives me an input in parallel with the same name. So now, firstly I need to make this in normally closed. Okay, so now we're going to try to simulate this. So like I told you before, when you click on the left side of your mouse, it's going to act as a push button. So I'm just going to click on A once, and now see, my output is triggered, and even this is triggered, and my output is continuously going to be high. Because as soon as I clicked this push button, my output was high, and it triggered this. So now it's just acting as its own recursive function, and it's giving
No need
supply to
to
itself.
press and keep it, right?
No, no, like as you can see, I'm not pressing my A right now. Okay, let's try it again. Okay. Yeah, so I'm just going to left click once on my A, and you'll see it go off instantly, and my output is going to be high continuously. Like no matter what I do to A, like even if I keep on pushing it, it's not going to be low. It's not going to get low, and that's why we have the switch B. Now, obviously, there's no other way to shut this whole rung. Like there's no way to get it out of power. So the only way is if I open this switch momentarily, and that cuts off the circuit. Did you all understand this?
Yeah.
Okay. So now there is another very important topic. Now this is used in a lot of plants and industries because it helps. So like I'm going to try to explain it with a simpler example. But usually in plants or something, there are many conditions. Like as long as this tank is running, this tank should not be running. Simultaneously, they should not run, or simultaneously maybe they should run. There are many conditions and terms that you need to satisfy. So in these kind of situations, interlocking is a very important asset. So interlocking is basically you're making two or more functions mutually dependent on each other. Like I said, one should be on and the other is not on. Like those kind of situations, interlocking is very useful. So I'm going to try to explain it with a very simple example. We're going to take two rooms. Okay, this M0.0 is my room 1 and M0.1 is my room 2. Let's just consider it as that. And this push button is for my first room, and of course this is for, I mean, the push button is for both of them. Okay, so I'm going to be giving one single trigger to both of them, and the condition is that the light in either of the rooms should not be on at the same time. Okay, so if I were to trigger my push button over here, this completes, like as you can recall, we just did this is latching. Okay, so if I give my push button a trigger here, my M0.0 is going to get high, is going to get triggered, and then it's going to become a recursive function. It's going to continuously give itself power. Correct. Now when this operation is on, this rung is shut and so is this. Okay, I mean this gate is shut and so is this. So it's a complete circuit either way. Now when I press this push button, I was getting input over here, but both of these are still open, so there's no point, like this is not going to get triggered. Okay, so now if I were to open my Q0.0, okay, so my this circuit becomes a closed circuit. This M0.1 gets triggered, this gets open, and since uh, this is currently high over here, this acts as a normally closed switch. This will become a normally open switch, making M0.0 shut. So when the light of this room is on, my this room is automatically going to turn off because this is linked over here, M0.0. So this, as you can see, this cross connection or mutually dependent function is controlling both of the rooms, both of the lights of the rooms, like with certain conditions that both of them cannot be on at the same time. And you're also like, this is basically a latching function again, and my output, like, so let's assume that my output is a fan. So this is a fan that's in my first room. So when this light is triggered and this is shut, the fan of room 0.0 is also going to be on. So when this and this are on, I mean when this is triggered, the fan of my first room is automatically going to be on, and if my second room light is on, then my fan of the first is automatically going to get shut. Did anyone understand? I mean, did anyone have any doubts about this?
No, I didn't get the last example.
The
Can you
fan,
listen?
like the third rung.
Yeah, you said something like if I on the fan in this, which one? I didn't get the cursor
Oh,
part.
okay. Sorry. I'll just repeat again. So you understood, if I press the push button here, the light of
Yeah.
the first room is going to be triggered. Okay. As soon as I press the push button, even this is going to get an input. But right now it's not functioning because my Q naught 0.0 of this is still it's not yet triggered. Sorry, this is 0.0. Oh, okay, my bad. So okay, let's go back to this rung again. My light of the first room is going to be on. Okay, we covered that. Now as soon as this light is on, this normally open switch is going to become a normally closed switch. Okay, so this, the fan Q 0.0 is going to be on and it's going to give a recursive function to itself. Now as soon as this fan is started, this circuit is going to be complete, which is going to trigger my M 0.1. So the light of
Why
my
is it
second room, excuse me, can you repeat that?
why is it complete? I mean, M0.0 is activated and that becomes a recursive function, and output Q00 gets activated. Then how does the second part get M0.1 get activated?
Because the push, like this all happens in a split second. This push button was still pressed at that time when all of this became zero. See, here we're
So
not adding.
these three are dependent on each other. I mean, if
Yeah,
one gets
yeah, it's
activated,
mutually
the
dependent.
second output also gets uh, this one, right?
Yeah, see, like how you can identify an interlock function is that if the output of one is controlling the input of another.
Okay.
That is the, and in latching, the output of one is giving input to another. See here, my output here is giving the input to the same rung, which is called latching. And in interlocking, it's controlling it in either way. See, here you can see a perfect cross between them, which is showing that it's very mutually dependent. And even here,
What will happen if first one is activated? I mean 10.0, push button 10.0. What all will outputs will get activated?
my if I switch this on and this on, in a split instant, my M 0.0 is going to be on. In the same instant, this is going to get triggered, and these two are going to get triggered. So first, see here, we're not adding any time lapse. We're not adding any delay. So you're going to be able to see it so quickly. What you'll actually be able to see is this, for a split second, your light of the first room will be on and your fan of the first room will be on. In that only second itself, these two will shut and the light of the second room will be on again.
Can you just say which one will on and what output will be on? I mean, if you press which one, which output will be on? That's it.
Okay, so see, if I was supposed to press my push button right now, I'll just go in the order that is going to happen. Okay,
Yeah. Okay.
so I'm going to press my push button. These two will be on.
Okay.
Okay, right now this is an incomplete circuit. This is a circuit. This is a complete circuit. So this is going to get triggered. This is going to get
Okay.
triggered. It's going to become a latched function and work by itself. Okay. Now second,
Okay.
because this is triggered, this is going to become a complete circuit. As soon as
Mm.
this becomes a complete circuit, my Q 0.0 becomes a latched function. It's helping
Okay.
itself. Okay. This becomes an open circuit and this is going to open up and this is going to shut. As soon as this shuts and my push button was on in that split second, my M 0.1 is going to be on. As soon as M 0.1 is on, it's becoming a latch function by itself. It's opening this rung and this rung. So in the end, only my this like even this is going to be off, but the last thing that you will see working is the room of the is the light of the second room.
Yeah. Okay. I got it.
Yeah, and like to explain it better, like if you want to try implementing this in your in trilogy, just you won't be able to see it that fast because we haven't added any time delay. But like right now, we'll teach you sums of timers and counters and try to implement it with a timer. Like you can put a time lapse of 5 seconds over here, 5 seconds over here, so you'll actually be able to see it counting down. Okay,
Yeah.
so Wait, my screen is visible, right, to everyone? If there's any issue, just let me know. Okay. Now, have you all studied muxes in DSD yet?
Yeah.
Okay. So, can anyone just tell me the basic concept of a mux?
It's if A and B, I mean the both the wires. If it's 0 0, then the first output, first one is the output. If 0 1, the second one is the output, and it goes on like this. Depends on the mux.
Okay.
2:1 and 4:1.
Okay, so that is correct. So here we're going to try to implement a 4:1 mux, which is also called a 4:2 mux, because we have two select lines over here. Okay, so basically what a mux is, y'all might have heard in 11 12 standard one to many and many to one function, right? So a mux is a many to one function because you have many inputs and you're getting one output. By this one output, I just don't mean the same repetitive output. It can vary in different ways. Like, see, here my output is just one Y, but Y also has different sections of it. But I'm going to have four inputs. So basically, how it works is, suppose just consider that there's the knob attached here, and it keeps on varying to which input it's going to take its power from. It might take from I3 at some time, I2 at some time, I1 or I0. It's a switch. It's a rotary switch which keeps on switching between these three according to whichever select line and whichever input you give. Okay, yeah, so like it's a data selector. It selects between several analog or digital inputs, and your end output is only going to go to one. It's not that this has many different functions in it. It's one function, but it's going to give you different outputs. So now we're going to try to implement a mux, 4 to 1, 4 to 2, whatever you want to call it. Okay, so um, so let's see the truth table of this. There are four inputs: I1, I0, I1, I2, I3. Like I said, it's a rotary switch. It's going to keep on switching between whichever input you're giving it. Okay, so the only thing we need to actually consider, which is in our control, are the select lines. Okay, whichever select line we choose, like suppose if I choose 0 1, the mux should know that the only combination that goes with 0 1 is my I1. Like let's consider this I0, I1, I2, and I3. So the only combination that's going to work with 0 and 1, it's I1, and at that time only this part of my input should be on. Just 1 minute. Yeah, so now I'm just going to try to implement it. Okay, so if any of you all have practiced the trilogy, you might be knowing how difficult it is to actually simulate certain programs. So there's a certain order that you need to follow. So we're gonna choose our first select line and an output, which is Y over here. Now just to make my process simpler, I'm going to continuously add S naught in parallel, and then I'm going to program it further. Since I have four conditions of 0 0 0 1, 1 0 and 1 1, they're obviously going to be four. Now I'm going to add my S1 as well. And the last one is input. So this is I naught. Oh, my bad. I need to add it in series. Over here, I'm just gonna continue the same thing. I1 and I2. And for the last one, I'm just gonna complete. Okay. So yeah, so this is our basic outlay. Now over here at 0 0, we know that only my I naught is going to work. So I'm going to program it according to that at 0 0. So that means when I'm not giving any trigger to both of these, and when I'm giving a trigger to I naught, my output should be 1. So obviously that means that these two need to be normally closed contacts. When I don't give them a trigger, they should be high. Oh, okay. This is done. Now for the second, for I1, it needs to be 0 and 1. That means this needs to be a normally closed contact and this needs to be, and S1 needs to be a normally open contact. Now for the third condition, S1 needs to be a normally closed switch. And the last one, obviously both are going to be 0 because I'm going to be giving both of them a high. Okay, so as you can, as I said before, that a mux is a many to one function. We have only one output, we didn't use four different outputs. So now I'm going to try to simulate this and let's try to implement all four. So now when I'm giving it 0 0 and my first input is high, I should get an output. So here I'm not going to touch S0 and S1 and I'm going to give the trigger to I at 0. So that's how I get my output as 1, which satisfies the first condition, and my D0 is 1. Now for this, I'm just going to continue the rest of them in sequence. I'm going to shut this. I'm going to give a trigger to my second input and implement 0, 1. I'm still going to get an output. Now I'm going to give a trigger to my third input and 1 and 0. I'm going to get the output. And for the last input line, which is I3, I'm going to trigger both of them. Yeah, and I get the output. Any doubt in this? It's a very simple thing. You just need to follow the truth table. Any doubts?
No.
Okay. So so a mux is a many to one function, and a demux is a one to many function. So does anyone have any idea of how you can implement the demux? Just give me an outlay. It's fine if you don't have the exact solution. Anyone?
You
Okay.
reverse everything. You reverse every switch.
Reverse every switch, but okay, but I said that my demux is a one to many, so I'm going to have only one input, whereas here I had four. So how do you suggest I inverse all of those?
No idea.
Okay, okay, fine. So the primary thing that we need to keep in mind is that we're going to have only one input. So let's just call it I naught. I'm just going to use the same names, and we're going to use S naught, S1, and a different output because here we have four different outputs in the demux. As you can see in the diagram, we have A, B, C, and D. So we have four different outputs. So we have to take care of each of those conditions. So now the first condition is obviously 0, 0, which means both of these need to be normally closed. So I'm going to implement that. And here we're going to use only one input, which is the I naught. We cannot keep on varying because the demux is only getting one input throughout its whole function. So I'm going to continue using I naught. It's not this one, and a different output this time. Even I was supposed to name it ABCD, but it's fine. And I'm going to implement 1 and 0 condition for this. Now second,
Why can't we branch it to the first one itself? I mean,
okay,
both
that's a good
I naught
question.
and I naught are separate.
Yeah, that's a good question. Like what you're suggesting is I could have kept this one I naught here and then made four cases along
Yeah,
parallel
yeah.
to this, right? Yeah, that's a good question. But the thing is that I need each of the outputs at a different rung. How I said before that Trilogy and Rexroth, both of these usually, I mean all PLC systems, if you don't give it a very clear output, Like if you're saying I could have given one input and then made parallel to all of them. The thing is, if you don't define it clearly, it just gets confused and it selects any random function that it like by any random probability you choose only one function to implement at that time. Like it's a very stupid way, but it's also a foolproof system in bigger systems. Like this is just a small circuit that we are implementing. That's why we think that we can do it in parallel, get done with it quicker. You'll see it in the lab also. Like we, after a lot of trial and error, we realized that Rexroth also works like this. Okay, so here I was supposed to, I need to shut this, and I'm going to make both of these normally closed switches. Okay, so now we're gonna go back to this. So this is my input.
Uh, Excuse me.
Yeah.
Did you X1 and X4 the same thing, like for the inputs?
Uh, wait, what?
So
Oh, I'm
both
sorry.
both of them.
Yeah, I didn't see that. Thank you for correcting me. I forgot. Okay. Thank you, whoever that was. Yeah, so in a DMUX, we're going to get only one input. So we chose our X naught and I mean our I naught. And in all of the cases, you're going in all of these four cases, these are select lines C1 and CO, you're going to get an output. But they're just going to be different outputs because these are your select lines, and you're going to have four output lines over here and just one common input line. So we're going to try to simulate this. Okay. So I'm going to keep my input 1 high because I'm always going to be giving it an input in the DMAX. And we're going to try 0, 0. Yeah, so at 0, 0, you can see that X1 is on. It's pretty obvious. Then I'm going to implement 0, 1. This condition is on. 1, 0. The second rung is on. And the last one, the fourth rung is on. Just ignore this for now, I didn't delete it. So this is the basic implementation of a 1 is to 4 or 2 is to 4 mux if you want to call it, because since we have two select lines we need to call it 2 is to 4. And yeah, any questions about this? Any questions? Okay, so now we're going to start with some sums, and Yash is going to take over now. Yash?
So, have you guys heard about encoders? Anyone?
Yeah, it's similar to Mux.
No, actually, they both are actually different. Similar, like, yeah, it reduces your number of inputs to output.
Yash, you're
So,
not
Answer
audible.
is like one.
uh, my voice was low now.
Just be a little
It's
closer to
as
the
if you're
mic.
talking from somewhere else.
So, Abhi, hello, Abhi.
Yeah, a bit more louder if possible.
Yeah, it's quite low.
Give me 1 second. I think I
Yeah,
will
sure.
change my.
Neeti?
Yeah.
Yeah, so I had a doubt that when we usually give inputs, they're always zero in the start. We have to flip them. Like when we
The,
make it red, it becomes one.
yeah, when like you're talking about a normally open switch, right?
Sorry, what?
You're talking about a normally open switch, right?
No, no, like the input, like, yeah, normally open, yes.
Yeah. So suppose this is my normally open switch. If I'm not touching it right now, it's going to be zero. As when I simulate it and give it a trigger, it's going to be high and it's going to turn into a normally closed contact.
Okay, so and normally close is usually a 1.
Yeah, normally closed is if you're not giving it a trigger, it's going to be a closed circuit and it's going to be a high. So it's going to be 1.
Okay, so like inputs, gates, everything is basically a gate which we have to trigger according to our
Yeah,
needs.
correct, correct. It's a switch which you just need to turn on and off. It's just that simple.
Yeah.
Okay.
Now I'm audible. Yeah, or else it's still low.
Yeah, it's cool. Yeah.
It's still low.
Just
No,
talk a
but
bit
like we
louder.
can hear it.
Okay, okay.
It's fine, people
So,
can listen with earphones.
uh, so you guys have heard about encoders. Like, have you studied right in DSD or somewhere?
Yeah, kind of like yeah.
Yeah, so encoders are generally, if you want to detect, there are like 7, 8 sensors. You have 8 sensors, and you want to check that which sensor is sensing, like detecting your signal. So your encoder will detect the signal, like for like if sensor 5 is triggering. So you will get your output as 101. Like it will display, it will give you output of the number which is high. Encoders are generally used for 7 segment display. Like 7 segment, have you heard about 7 segment display? Hello, hello, hello. Am I audible?
You're actually barely audible. That's the problem. Nothing else.
I think you can use your phone for audio.
Yeah, I'm doing that one. So can you guys hear me now?
Yeah.
Yeah, this is better, right? Or should I talk more louder?
No, I think this is sufficient with your phones.
This is sufficient. Okay. So yeah, encoder is generally like you want which line is high. You want to know which line is high, so you will get the output in your binary output. Like if you have your output zero, if your output zero is high, then you will get the binary output of zero, which is 000. It's like that's the gist of it. But generally, encoders are not used like this. It is like 7 segment display. Have you heard about 7 segment display?
Yeah, it's in calcium.
Yeah, so it's generally used in 7 segment displays. Encoders are generally used, but I will just show you 823 encoder because 7 segment is can be done, but it's difficult. So this is the truth table. Like no need to know truth table. So first I will show you. So there are 8 inputs because it's 8:3. 8 inputs and 3 outputs. You can just, if you want, you can at the start also you can just label your all your inputs and outputs, so it will be easier. So these are 8 inputs. You go to outputs, change the outputs. So it's easier. You can go here, just specify all your things, whichever you want, and then you can just start it. It will save some time. So first I will show you this. Yeah. So if your run 3 is high, so you should get the output as 3. So in binary, can someone tell me what is 3? Anyone? Hello?
011.
No? Ah, 0, 1, 1, yeah. So it's 0, 1, 1. So what should you should get A2 as 0, A1 as 1, A0 as 1. Because this is your MSB and this is your LSB. So you start. So for your A to be high, your A2 should be high. Then which can someone just give me which all uh, which all elements here is high? Then A2 will be high. Like which one of these elements gets detected? Then A2 will turn high. Any guess? Like could be. Yes, no, नहीं आता तो ना तो बोलो.
No.
Okay. So yeah. So if you want your A to be high, then it should be uh, like uh, the number should be higher than 4 because this has 2 to the power 2, which is 4. This has 2 to the power 2, this has 2 to the power 1, and this has 2 to the power 0. So if you want this bit to be high, it should be 4 or higher than 4. So let's implement that. And also, you can implement encoders in two different ways. One is like highest number active or lowest number active. I will show you both. Yeah. So for A naught, yes, A2 4 should, if 4 is high, then you will get it, or else 5. So if any one of this element will turn high, then A2 will turn high. Similarly, for A1, like it should be if you want A1 is high, then it should be your A1 has value power 2, so it should be 2, 3, 5, and 6 and 7. So this is here. Can someone tell me for A naught, like when will A naught will turn high? Anyone? ठीक है. So A naught has value 1, right? So it should always be turn high on odd numbers. So your odd numbers are 1, 3, 5, 7. So this is your encoder run. So your Y naught is high, it's showing low, like no connection. So if your Y1 turns on, this is your binary in like in binary this will show 1 0 0 1. Then in let's assume 5. So 5 in binary is 1 0 1. So it will show you your 1 0 1. 6 is 1 1 0. 7 is 1 1 1. You can see it. So this is your like zero dominant encoder. It is named as zero dominant encoder because if there is no input, you will get as zero, which means like nothing is there. Still, it will show zero. This is called a zero dominant encoder. Now I will show you eight dominant or high dominant encoder. Can you guys see what I did here? This is the lower part. 1 second. Circuit. Outputs for same name. That's why. Uh, did you guys see what I did here? Like these were in parallel and they were normally open. So like whichever were not here, we just changed it into normally closed, and that's all. That's all in series. Let's show you this. So this, as you can see, it is 7 dominant, like high dominant. If there is no signal, you can see 7 is showing, and the above was zero dominant. If there is no signal, it's zero will show. Now I will show you two. Yeah, both A1 and A2 is same. So like circuit works same, but the logic is one is zero dominant and another is seven dominant. And this is the output. Any doubts? Hello. Am I audible?
Yeah, no doubts. Understood.
No doubts, right? Hmm. This is your encoder, decoder. So decoder is just similar to encoder. Just your the three rungs are like your output will be your input and input will be your outputs. Like it sounds simple, but it's not like directly the same thing. So your this is your select lines. You can say select lines will send the information. This is your enable, and this is your output. So in this, here whatever value in binary will come, it will show that number as high. Like so if here it is 110, which is in binary 6, so your output D6 should glow. This is your truth table. Uh, so here there are 8 different outputs. So like we did in Dmux, each output should have its own rung. So we will be doing the same thing. First, you have 3 inputs. And 8 outputs.
You should have 8 ladders, right?
Yeah, 8 different ladders because there are 8 outputs, right? So each
Yeah.
output should have its own ladder logic run. You can also like copy the circuit and then paste it. It saves you time and save time for me also. One, two, and then So here, if you have no, like, if your all the select lines are low, which means it's 0 0 0, then your output should be high. So when it's 0 0 0, so when this will be like when you have no select lines, then your output A should be high. The same thing like when S1 is high, this is first S3. Can someone tell me what I have to do for S5? Like you can just see by looking at the pattern. But anyone, which one should be normally closed? तुक्का भी मार लो.
This is from what to what coding, like binary to like.
Yeah. So like here you
So
have
that's like it should be 0 1 1. If I'm right. So
yeah, 5 should be 0 1 1.
no. Yeah.
Oh,
Okay.
like 1 1
No.
like
1 0 0. Right.
yeah,
No
like
one. Okay.
yes.
Sorry. Sorry. Wait.
Yeah, yeah, you say. Like you were saying 0 1 1 as the answer, right? Like this, no?
Yeah,
You were
this
saying
should be.
this.
Yeah. Yeah. Yeah.
Yeah.
Somewhat. Like.
So like you had the doubt, right? So encoder is like you have some n inputs. So your n input lines will turn into two to the power n outputs. So as you know, binary is like in binary you can from n bit, like if you have n bits, you can create two to the power n numbers in binary. It is the same logic. So you give your like binary input, like if you want 4, so you give your 1 0 0, and this will give you the fourth line output. It will just trigger this. I will show you.
Did you make 1 0 0 for like A1?
A1, it's 1 0 0. Like
Okay.
for A1, your S not should turn high. Like I will show you.
Like, are we using like binary code?
Yeah, we are using binary code.
So shouldn't it be like 0 0 1? Why do we take 1 0 0?
See, you can see A2, A1. See the naming. This is like S not. I have just written in order is different, but this is the MSB. S2 is the MSB. This is LSB. S not is LSB.
Okay, so like it's right to left.
Yeah, just
Okay.
my naming order was so you got confused. Just
Yeah.
see the naming, right? S not is the LSB and S2 is the MSB.
Okay. All right.
So yeah, when there is no inputs, your that is 0 0 0. Your output 0 should be high. So when I turn this is 2 to the power 2, which is 4. So your output 4 should turn on. This is your binary 5, so 5. This is your binary 3, so you can see 3. And this is 7. So 7. Any doubts?
Huh.
So, is it a convention to name it like that only, like 0, 1, 2? Like,
No,
is it a
like
convention to
if
read it
you
from right to left?
you can just name it
So we can
anything.
put the
You just
output S1 in names that I mean we can change the outputs, right? I mean inputs.
yeah, you can change it here. You can give any name, but you should like
We can
for
make the MS.
simplicity.
You did the MSB as the last one. I mean we can put even the reverse order as my friend said.
Like yeah, you can change here. You can change anyway. For say just say for you two only.
We can put S naught as last one and S2 as the first
Uh,
inputs.
yeah, just sure.
Yeah, okay. I got
You
it.
can do like this also. Like I made a mistake. I did like this, but you can do like this. So for understanding, it will be easier. So
Yeah,
this will be your
okay.
MSB, and this will be your LSB.
LSP. Okay.
Okay, right, I understood.
This is deeper. Yeah. So timer question. Have you guys tried timer? Like किसने घर पे कुछ practice किया? Last class we taught you like have you guys just opened the software?
लास्ट क्लास तो बेसिक गेट्स हुआ था ना.
Gates try किया था?
हाँ वो हुआ था.
Okay. So I will teach you how to use timer first. So your input T. So now if you have to click your output, then click here. You will see a timer thing. Press enter. Just name it anything and here set value. So values here are given in like 0.1 second. Like each one is here one represents 0.1 seconds. So if you want 5 seconds, you have to write 50. So this will be your 5 second timer, and if you want to use it, and yeah, you can use timers as input. So your when this timer reaches your value after 5 seconds, then this will turn on. Let's see. Yeah. So this is T on timer. You guys have do you guys remember T on timer? So in this software, there is one thing you can't use T off timer. For T off timer, you have to write a code and which we are not doing here. But in Rexroth, there is pre-made T on timer as well as T off timer. You can use both the timers in Rexroth. So once you turn this on, as you can see, the timer here is clicking down. So after 5 seconds, once this reaches, then your output will turn on. So it will turn off. So as soon as you reach here, like, did you guys understood how the timer works? Do you have any doubt?
So if we are implementing like anytime, should we actually use the first line basically? Like the first line you gave A and to
See,
a timer, right?
A is your input. Uh, like
So
last time we
basically,
showed
just
you.
like a open circuit, it's just an element, right? The timer.
Yeah,
Okay, fine. Understood.
Can you repeat the timer once?
yeah. So like, should I explain in ladder logic, right? So your timer is. I'll show you again. Yeah, for creating a timer, like you have an input. Say example, your input is A, and you want your output turn on after 5 seconds. After turn, like once you turn on A, your output should turn on after 5 seconds. So you have to use a timer. Go in timers. A. Your set value is in zero point 0.1 seconds. So for each second you want, you have to multiply by 10. So I want 5 seconds, so I will multiply by 10. So 50 seconds. Now this is your uh, just your input to the timer. So now you actually in Rexroth it is different. You will have a different block only, where your input is there. Then there is a timer block, and your timer will have an output itself. But in this software, there is no output to the timer, so we have to make a new run in which we have to label the input as timer and then output as O and run. So once your input starts, your output will not start. After 5 seconds, your timer reaches the output, then it will turn high.
Why
You
should we
guys,
make a new one? You said something.
yeah, new one because this software doesn't support, like in Rexroth, there is a big timer block. Like there is a block. The timer block has like timer block has three pins. One is input in Rexroth, I'm saying, and not here. It will have input pin, it will have output, and it will have a reset. This thing doesn't have reset also. So yeah,
Now,
your
if you
input,
add multiple gates, if it has two or three, then what will you do?
what, two or three?
These gates, A, B, C as input. Suppose it's like in the first ladder itself, there are A, B, and C, and one is closed, one is open. Then, if you put a timer like this, what will happen then?
Generally, it will not happen because your timer is used to a specific gate. But like I will show you.
So, one timer for one gate.
Yeah, like for your gate is your input. For each input, there will be some certain time of delay. So after that delay is passed, then only your input will turn high. So like here you are saying your input is A and your like output for A is O, and this is just transition. Like you want a delay, like example. Huh. Have you guys like seen some lab in. Okay, leave it. Um, like if you want to for like input, you will get like एक input के लिए तो जो explain you guys want 5 second delay. So for your that input you will get once the input is high, after 5 seconds your output will turn high for that input. Now you can use this output as your input for the like for latching. Like after this you want to turn on your machine, some example motor. If you want to turn on your motor, so you will use this output to your. So now I will show you a similar thing. So once this reaches your 5 second, your O will turn on, due to which your motor will turn on. But here, like there are some more complicated problems. I will like we have here. I will teach you. But did you guys understood how to use timers in this software?
Yes.
Okay.
Yeah,
So
but
in
I had
this,
a doubt. Wait a minute. It's like I asked you something that if there are two gates, I mean, if there is A, one open and one closed B. Yeah, one A and one B, and how to add timer for this one? Two inputs. B
like
besides.
uh,
Yeah, this is closed.
Like A is different input, B is different input, right?
Yeah, so how to put a timer for this then?
So you will have, this is actually, you will have a separate timer for A and a separate timer for B. So you will have like this. This like timer latching, you can use this, like you were saying, you can use this also. Then this timer actually depends upon two things: your A being high and B being low. So you can just see here. So once your A is high, you will see your timer going. But as soon as your B turns on, your timer stops because your circuit is broken, and your timer will just stop until and unless B is again low. Like you can use this in problems if you want. So in this question, when a switch E is pressed, you should activate your motor Q1 after 5 seconds and your Q2 after 15 seconds. And your motor Q2 should run for 5 seconds, and after 5 seconds your Q2 should go off, and of that, of like once Q2 goes off, you have 3 seconds Q1 should run, and after that Q1 should turn off. I'll just explain it. This is your A. Timer T1. So after 5 seconds, your Q1 should turn on. Now for logic for Q2. Q2 should turn on after 15 seconds. So you will use A. Actually, you can use here also. Because the input is same, so you can just use another timer in parallel. And the time starts at the same timing, so you can use this only. And it's for 15 seconds, so we write 150 here. So Q2 should start after 15 seconds. Now Q2 should run for 5 seconds. So it should run for 5 seconds. So here it should turn on after 15 seconds and run for 5 seconds. So we will add one more timer which will count 20 seconds. Actually here I was going to use a T off timer, but this system doesn't have a T off timer. So we have to do this way. T3 200. So now it should turn off after once this time is reached. So we will add this and invert it. Now what's more condition? Once Q2 goes off, after 3 seconds, Q1 should also go off. So for that, so Q2 goes off. or 3 seconds. See, Q2 will go off once T3 is high. So once T3 is high, your this timer will start counting. For after 3 seconds, it will turn on. So you can use this here, invert it, simulate. So once you turn on your A, it will start your timer T1 is counting. All these three timers are counting. So once T1 is reached, your Q1 will start running. And once your Q2 is reached, your Q2 T1 T2 is reached, your Q2 should start. See, it starts. And the timer T3 reaches, your Q2 stops. And after 3 seconds, Q2 also stops. And any doubts? It's a bit tricky. Any doubts? हाँ ना कुछ भी. Am I audible? Hello.
Yeah, yeah.
Do you have doubt or should I continue?
Listen, since it's already past 7 o'clock, I think we'll just give you all the questions for the rest of the question. We'll give you all the questions, the sums, and we'll give you all the solution later whenever you require it.
I think I will explain them counters also, or else they can't do the solution.
Okay,
Just a
fine.
second.
So then after counters, we'll wrap it up.
Yeah, yeah.
Okay.
So I will just teach you how to use a counter. You have no doubts and timers. So you guys know timers. So I will give you one homework. Make a T off timer using T on timer. Like in this, how to make a T off timer. Just do some brainstorming and next class give me the answer. So now, one second, I will show you how to use counters. This is your A. Yes, see, your counters has a some set value. This is your down count. This is your down counter, so it will count down, and you have to give some set value. So if you give a 10, it will have a 10 value. And this will be this is also same thing as we are doing in timer. Like you don't get output directly. You have to use the counter name as the input. So this is your counter. Your counter detects a pulse. I will show you. Your counter will detect once it receives a rising edge. Do you know, guys know rising edge, right? So rising edge means like once it detects high, it will count. So once it detects A is high, your counter will count, and it will count one less. Like sorry, it's a down counter, not up counter. My bad. It will count, and this will turn one less. See, once I turn this, it will still not count. It will just count your rising edge. So I press once, it counts a edge pulse. It counts another pulse. See, once it reaches 0, your counter will start conducting and it will have output. In your extra, there is in this you can't do one thing. In this, see, once your counter reaches the value, once your counter reaches 0, if you want to turn this counter back to 10, you can't do this in this software. But in Rexra, there is one more thing: set coil. It will set your counter value to back to the 10, so you can count the things again. That's it. Any doubts? Counters could be.
Is it somewhat similar to what a timer does?
It is similar, like timer. See, for timer, I will show you. For timer, your input should be high continuously. But for your counter, like your input should be high, then only your output will be high after certain amount of time. But your counter counts your trigger pulse. Like your counter counts the pulses. Like value. Yeah, the circuit looks might be looking similar to you, but the function of both things are different. Similar. See, your counter will detect your rising edge. Means you're positive. Like when your count goes from 0 to 1, your counter will detect and your count value will decrement. It will keep on decrement until it reaches 0. Once it reaches 0, yeah, sorry. So once your counter reaches 0, then it will start triggering. But for your timer should like your input should be on, then only your timer will start counting. But once your input is off, your timer can't count. Like it will not conduct. See, once your timer reaches a certain value, then it will start conducting. But for your counter, it should count your rising edge that number of times with a set, like you have some set value. It should count that much set value, then only it will conduct. Is your doubt solved?
Yes, 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 sir.
So yeah, you just try making off timer using on timer, and your counter is here. So this is the question. Just try. If you don't get it, we will just share you the answers, and we can explain it in the next class also. So just see this, or else we will send you or take screenshot. कोई doubts है या or else should we end? Any doubts?
No,
No
bro.
doubts?
No.
Nothing, nothing.
Okay, okay. चलो.
Okay.